Hi there, this is Jonathan Bartlett from theStatsGeek.com. In this very short video I'm just going to look at how the Hosmer-Lemeshow goodness of fit test for logistic regression can be performed in R. So I've loaded R here and I've got a script file here, and the first part of the script file is just going to be used to generate some artificial data to illustrate how to perform the Hosmer-Lemeshow goodness of fit test. So the code here is just to simulate some data. You wouldn't need to do this if you had your data to hand. By the end of this little code snippet, what we've ended up with is a data frame which I've called my data, where I've got a continuous, two continuous covariates x1 and x2, and a binary outcome y. And the first thing then that we need to do is to fit the logistic regression model that we're interested in fitting. Do that using the GLM function, so I'm going to define a new object called mod. We then have GLM, y is the outcome variable, the binary outcome. x1 and x2 are going to be covariates or independent variables. I then reference the data frame, which is I've called my data, and then specify the family as equal to binomial. If we specify the binomial family, we get a logistic regression, the logit link by default. So let's run that. And R has run that. If we have a look, we do summary mod, we can see the fitted logistic regression model, the estimated log odds ratios, standard errors, Z statistics, and p-values. But what we now want to do is perform the Hosmer-Lemeshow goodness of fit test. Now, the GLM function in R can't actually be used by itself to perform the test, so what we're going to do is use an external library, the resource selection library, which implements the Hosmer-Lemeshow test. So let's load up that library, and then performing the test is really very easy. I'm going to call a new object to just save the results of the test. The function is hoslem.test, and the arguments are the binary outcome, and then the second argument is the fitted probabilities from our logistic regression, which we can extract by typing fitted and mod. And then the last option that will commonly be used is to specify G, the number of groups to use. So the Hosmer-Lemeshow test, the way it works is it divides the dataset into a number of groups according to the fitted probabilities that the binary outcome is a 1, and then it compares the number of observed 1s and 0s with how many would be expected under the model fitted values. And G here specifies the number of groups to divide the dataset into, and 10 is the sort of default number which is often used, and that's what I'm going to use here. So if we highlight that line there, it's performed the test. If we want to actually see the results, I'll now type HL. We've got Hosmer-Lemeshow goodness of fit test. This is the chi-squared value. Here I've got a value of 4.8. It's on G minus 2 degrees of freedom, so I've got 8 degrees of freedom, and I've got a p-value here of 0.8. Now if this p-value is statistically significant, for example if it's less than the conventional threshold of 0.05, that means that we've got evidence that the model doesn't fit the data well. So there's evidence that the model is fitting badly. I've got a non-significant p-value here, so I've got no evidence that the model is fitting badly. So we might well conclude from that that our model fits well, although it's important to remember that these goodness of fit tests, these sort of global goodness of fit tests, a non-significant value is not proof that your model fits well. It just means that you haven't failed to reject the null hypothesis that your model is correctly specified. Quite a nice thing to do after performing the test itself is to actually look at the observed and expected values which are used when performing the Hosmer-Lemeshow goodness of fit test, and we can do that quite easily using the HL object that we defined a moment ago from the hoslem test function. And what we can do is just join up the HL $expected values, which are the expected values in each of the 10 groups, and look at those against the observed values. So I've done cbind HL dollar expected, comma HL dollar observed. And what we get if we look at that matrix is on the left hand side we've got the ranges which have been used to divide the data set of the fitted probability values. So the first group are those individuals in the dataset, those units in the dataset, which have a fitted probability between 0.023 and 0.984. The next group, this range, the next group, this range. And the way that those groups are formed are into groups of equal size. So because I've specified g equals 10, these are deciles of the fitted probability. What we've then got here, we've got the number of observed ones and noughts in the binary outcome y in each of these 10 groups. So in the first group, there were no ones observed for y. All of the values of y were 0. There were 10 zeros. Similarly, in the second group, we've got 10 zeros and no ones. And then as we go down, what we can see is that there's a general tendency towards fewer zeros and more ones. Columns here, y hat 0, y hat 1. Y hat 1 is the expected number of ones in the lowest group, the second group, the third group, the fourth group, etc. And the basis for the Hosmer-Lemeshow test is a comparison of the observed number of ones and zeros with the expected number of ones and zeros. And the way that these expected numbers are worked out is that in each of these groups, the fitted probabilities from the model are averaged across the individuals in each of the groups and then multiplied by the group size to calculate the number of expected zeros, the number of expected ones in each of the groups. And it's quite a nice thing just to look at this, just to see how different the observed and expected values are. Of course, even if you've got a perfect a model that's correctly specified, there will be some discrepancies between observed and expected due to sampling variability. Okay, so that's how to perform the Hosmer-Lemeshow test for goodness of fit in logistic regression. For more information on this, you can look at the corresponding article at thestatsgeek.com.